And now that we've looked at a lot of evidence that supports the theory of evolution, such as we said DNA, biochemical comparisons and relationships, remembering that the more similar DNA is, that infers a much more closer relationship in terms of evolutionary trends. We can compare anatomy, physical structures, etc. And once again, more similarities, which we'll see in a little bit, infer evolutionary relationships. But we want to take a look now here with fossils and focus a little bit more on fossils, because several students have expressed concerns. How the heck can this dead, quote-unquote, rock thing tell me about evolution? I thought only living things could evolve. So let's take a look at what these are and how they work, because the premise is pretty simple. So what a fossil is, now we can see here's a fantastic example of a fish fossil. Remember that it essentially just traces of an organism that was once alive. Now we need to get really lucky for a fossil to form, and how they form, because if we know what to look for, we can learn a lot from them. Because essentially what they are, when an organism dies, that becomes buried in sedimentary layers of sand, silt, mud, and rock. And if conditions are right, if we're lucky, we can actually mineralize these structures, and what's left over just, for the most part, the bone structures. We can see traces of mineralized skin as well, and we can learn a lot about the form and function of that. And if we can compare them accurately with some inferences, we can trace evolutionary relationships. So recall that these are dead organisms that were once alive that have now been preserved for us to go back and look at. That can be tens of thousands, in some cases millions, hundreds of millions of years old. So the first most important one is, how do we know how old a fossil actually is? We can't ask it its birthday. We can't look at a birth record. How do we tell? And there really are two different methods here. One that is called relative dating, and one that's actual, in essence, a simplified term, numerical dating. Now, if we look here, each one of these rocks or bars or colored sections is a different layer. As it says here, dating of volcanic ash. Now, it may be from volcanic ash, it may be mud or silt, but it's a hardened layer within digging downward. Here's the Earth's surface, and as we dig down into the ground, we get deeper. Notice they get older. So that's really, really useful. And we'll look at each one of these, the radiometric or numerical dating, or relative dating. Relative's a little bit easier. Radiometric, actual numerical dating is a little more accurate. But if we look at that, the radiometric dating, in essence, is the fact that all organisms contain trace amounts of various amounts of elements, obviously. And the secret is here that each one of these elements can radioactively decompose, decay, and turn into essentially another isotope, a radioactive element itself as well. And the secret here is that we can measure what is called the half-life of these elements. So in essence here, we know that for potassium-40 to decay into argon-40 takes 1.25 billion years. Wow, that's a long time. But what we can do is measure the amount of argon-40 in a fossilized structure, and based upon that we can extrapolate and figure out approximately how old, if for instance if 1/2 of the molecular makeup of that is potassium-40, 1/2 is argon. 1/2 of that is turned into argon-40. That much time has gone by. So it gives us still a rough estimate, but a good idea, so in which scientists can say that fossil is approximately 55 million years old or 21 million years old. So that's pretty useful. The other one with relative dating, I'm going to ask you to try in a second, is simply speaking, we can use the phrases older or younger. We can tell by relative dating and layering approximately how old specific fossils are in relation, relative to one another. So let's go ahead and try one here. I have two different strata layers, two different layers of Earth. Here's the surface. Remember, as we go down, remember the estimation is that, or approximation rather, is that we get older as we go down through the layers. So here's from a certain area, layer number 1. Here's from area number 2. Now we can see that we have letters here to reference each layer. Notice that we can compare the two, and because the layers here, B and D, are exactly the same in terms of their makeup, we also can note that these fossils are the same as well, the same structure, the same sizes. So these two layers are the same age. This fossil is the same age as this fossil. Now, a couple of quick questions that I want to have you pause and try to answer here is, which fossils here by letter are the oldest? Go ahead and take a second and quickly try and figure that out. So hopefully you were able to figure out that because of the layering being the same and the fossils being the same, that C and F are the same, and also that C and F, being the lowest here, are the oldest. But now I've got an even trickier question for you. What we need to determine here is which fossils are older, A or E. Now, if we go and look here, we can see that fossil A is higher up in the layers than fossil E. E, we can infer this came, evolutionarily speaking, prior to, earlier in time than D. Because, for in its simplest format here, that looks like a -1, sorry, this fossil came after, it's above B. This one is younger than this guy. So we can then infer that fossil A, right here, relatively speaking, is younger than fossil E. You can see that this is actually a fairly useful trick as well in an evolutionary biologist's arsenal. And one other thing that we'll look at here to end with fossils, because it's fairly simple, is that if we had some similar fossils in layers, we can actually almost create what amounts to an evolution flip book, if you will. We could actually see, like, for example, let's say that in, well, perhaps this layer up here in D, we found something that looked kind of like what was in E right here, but instead it looks like this and has a couple of legs on it. It's a little different, or appendages, if you will. We can infer that this guy right here evolved over X number of millions of years, however old the differences are between ages here, and possibly evolved into this structure. It acquired these appendage traits. So we could actually get a flip book of ordering, and we can infer how species have evolved over time. Obviously, the older ones evolving into the younger ones, which again can be extremely useful for us if we know what evolution is and where to look. So let's end by taking a look at that, how we would piece together fossils to infer these trends. And the great example is one that several students brought up in class, in each section actually, which is kind of interesting, the evolution of whales. I'm assuming from videos, from TV, people have inferred that whales evolved. Some people said that whales came from dinosaurs. Some people said that whales, some students said they even came from wolves. And that's interesting. So let's take a look at this and see how this evolved. Notice up here there's a timeline. We have starting here is modern day. Going backwards, these are in millions of years. So let's jump back to 55 million years ago rather. Scientists found fossils that they've dated to about in that time period, and what they found were fossils of, once they pieced them together, of these particular organisms up here. Now those aren't whales, obviously, but we've dated them back to this time period, and they have some traits that give them, as we find later fossils that we find and we date them to be a little bit younger, and obviously 35 million years old is pretty old. But notice that we can actually, and not all these structures are shown here, but notice that this Ambulocetus, tough names to say, looks a little bit like Pakicetus, and we have them branching, that these guys shared, possibly a common ancestor, but that their skull bones are very similar. In fact, many similarities even to modern day whales. But notice that they've realized that the hind legs, the appendages here, have changed. They now are more flattened-like, more streamlined body. Even though this was streamlined, this creature appears to have aquatic tendencies, if you will. And all we have to do is keep acquiring. The more fossils we find, the more pieces of the jigsaw puzzle, if you will. And if we order them correctly, we can actually see how whales have evolved. The earliest whale fossils date from about 38 million years ago, approximately, give or take, is when Odontocetes and Mysticetes are two modern-day classes of whales, or excuse me, orders of whales, rather. We'll end with classification later on this year, how they have evolved. So fossils, you can see, even though they're dead, fossils don't talk. Fossils tell no tales. If you know and understand natural selection and evolution, you can read a lot into that, and you can actually see how modern-day species have evolved over time. Very, very useful tool. Now, keep in mind, I want to end with a caveat that these concepts we're talking about take millions of years. This is our concept of what we've been emphasizing in class, which is very, very important that we remember this, that this is an example of macro or big evolution. What we had talked about before with our examples of bonk birds and species populations changing slightly, that's a little different. That is micro evolution or small. But if you think about this, if you keep adding up micro, little changes with more little changes with more little changes and more and more and more and more and more, eventually we end up with, for example, if we start with organism A here and we keep adding more and more changes, eventually we end up with two subgroups or subpopulations that are so different they actually become two different species. And that's, for example, what has happened right over here. We've acquired these traits. So macro is the one that people have a tough time with. Fossils show macro evolution, but keep in mind it's the micro, the small little changes in populations that lead to macro evolution. And that's a very, very important thing to remember. So now that we've watched this, I'm sure you and I will chat. We'll go over your note sheets and any questions you may have. And I want to have you play evolutionary biologist and try working with some fossils to see what kind of inferences you can make. Have fun.